Pilot 1B, catalytic converter via EBM.
I'm Timo, I work for KTH in Sweden, and we were tasked with pilot case 1B for the diameter project, which is building a catalytic converter using electron beam melting. Electron beam melting is a relatively new additive manufacturing method that uses directed electron currents to melt powder and create parts out of that. While traditionally laser powder bed fusion would be a very strong contender for a use case such as this one, it's not possible in this particular case because the high reflectivity of copper forces us to pivot to different technologies. This is where EBM comes in, where reflectivity does not really play a role at all. We also have a lot of hidden channels in the part and a lot of small features that would be hard or nearly impossible to achieve using traditional manufacturing methods.
Why is electron beam melting the right process for pure copper in this application? What makes it both promising and technically difficult?
The right process comes down to what I said during the introduction, which is that both the features and the material force us to adapt to new methodologies. It's a very challenging process because parameter optimization has not seen much research, especially compared to traditional manufacturing methods. At KTH, we've been focused on this topic for a long time, and I think we developed a set of parameters that can produce really nice looking parts, such as this one. But of course, there's always room for improvement.
Pilot 1B is one where the alignment with circularity is still being defined. We plan to communicate this openly. Are you comfortable speaking to the open questions as well as the progress?
I cannot say very much about the progress, but circularity is of course a very big topic for KTH. One of our key pillars of being states that sustainability is a goal in all of our projects, and circularity is one step closer to this. In this particular case, our LCA has shown that a lot of the energy consumption comes from the actual production of the powder, which unfortunately is out of our hands. But we can also make some progress in optimizing the EBM process to hopefully be just a little bit more circular in the future. We also reuse any powder that isn't used for the build case, so we have very little waste in that regard. That is one of the main advantages of additive manufacturing methodologies compared to traditional ones.
KTH also leads Work Package 7 on impact creation and the vision of a circular manufacturing institute. How does a pilot like this feed into that longer-term ambition?
While my colleagues are more focused on these efforts than I am, I would argue that the successful creation of pilots like this and the ongoing research with that can provide the databases that is needed to feed into a larger ambition, such as the ones mentioned by you. What we're doing here is not only produce the part, but also measure the energy consumption along every step of the way and try to develop models to predict it for future use cases. So we can have a data-based decision model that can allow us to choose the right process for the right part.
What does a successful outcome look like for Pilot 1B by the end of the project, technically and in terms of what it contributes to European research?
I think that depends very much on who you ask. Myself, as an AM expert, I'm very happy with the outcome I'm holding here in my hand, a very nicely shaped part. But of course, that's not the goal of the project. So I would say a successful outcome from our side is both the ability to produce parts in this environment, to gather the data while we do it, and to work with the data and our colleagues in the Diameter project to create long-term models that can allow us to create parts like this or any future use case in a more sustainable and circular manner, and give us a decision-making point for which technology to use and how to use it efficiently.